All right, so we made this observation that if we look at the Fourier transform of the convolution of two signals, it's actually the pointwise multiplication of the amplitude of the first original signal times the corresponding amplitude of frequency of the Fourier transform of the impulse response. Boy, that's a mouthful. But you could just see, look, I multiply this thing by this thing, and I get this thing. So this is the discrete Fourier transform of the original signal. This is the discrete Fourier transform of the impulse response. Multiply them together, and I get the discrete Fourier transform amplitude of the convolution. So now I want to actually prove that's what happens. And I'm going to prove something a little stronger. So here I was just looking at the magnitudes, but I want to show something a little more. So I'll say to prove. What I want to show is that, so let's say let x and h be two signals with n samples, and let y equal x convolve with h be their convolution. We're also going to assume that x, h, and y are all periodic. This is going to make the proof a little easier. There's ways to get around this, which I'll discuss at the end of this module, but for now we're going to assume that x is periodic, and also that the impulse response h is periodic, which I know is a little strange. I mean, here I was just supposed to have the samples in the beginning be non-zero and then the rest zero, but it's just saying this will repeat itself. So we just get an infinitely repeating version of this echoing thing. Okay. But anyway, okay, so we're going to assume they're all periodic. Let's also just let x of k denote the DFT of x. We'll let capital H of k denote DFT of h, and capital Y of k denote DFT of y. Then what we want to prove is the following. So proposition. What we could say is that y of k is simply x of k times h of k, where this is actually complex multiplication. So we're talking about complex DFT the whole way through. So here I was just looking at the amplitudes and saying, oh yeah, it looks like they're multiplied with the amplitudes. But I can actually say even more. I could say that as complex multiplication, so using the rules for multiplying complex numbers, y's DFT, the convolution's DFT at frequency index k, is actually equal to x's DFT at frequency index k times h's DFT at frequency index k. Okay, so how on earth do we prove this? Well, let me just go back to the definitions of the DFT and the definition of convolution. And I'm going to just do some algebraic wrangling. So, okay, so I'll say proof. Let's do it. And this is a neat proof. So I want you to pay attention. All right. So let me start with the definition of the Fourier transform. So really, I want to compute y of k. All right. So that's y. So I'm taking the convolution. Sorry, so I'm taking the dot product of y with this phasor. Okay. Now I recognize that y actually represents a convolution. So let me go ahead and plug in that convolution. Y is the convolution of x with h. So I can just plug in for y the formula for the convolution of x and h. So that would be this sum. So let me put that in parentheses so I know that I have to compute that entire sum before I multiply what's on the outside there. So let me just write what I'm doing. So I'm going to plug in the formula for the convolution. And I get this. Okay, what do I do now? Well, so here's where I have to do a little trick. So actually, I can switch the order of the sum. Well, actually, before I do that, okay, notice that I can use the distributive rule. This is on the outside of this whole sum, but I can actually distribute it through and associated with each term here. So let me just use distributive rule to group the phasor term with the inner sum. Okay, so I can do that. Cool. So I got that in there. All right. Now I want to do something a little weird. So what you notice is this really, if I was going to implement this code, this is really like a nested loop. Where I loop through n in the outer loop, and I loop through j on the inner loop, and I sum a whole bunch of stuff up. And I sum n times j terms up. But it doesn't actually matter what order I do the sum in. So what I can do is actually, I can switch the order of the summation. And make, so these are all terms, you know, here's every term. It doesn't matter if I sum them over j first and then sum each of those over n. I could sum them over n first and then sum all those over j. So let me make the outer summation be over j. And the inner summation be over n. So this is actually, okay, so I'll write this. So all I'm going to do is switch the summation. So I'm just going to pull this, just put this on the inside. And I don't need the parentheses anymore because I know everything is grouped there. Okay, so how's that look? So I just switched the order of the summation. So this is analogous, for those of you who've had Calc 3, this is analogous to the Fubini theorem for multiple integrals, for switching the order of integration in multiple integrals. But if you haven't had Calc 3, that's fine. I just wanted to throw that out there. You can just think of this as loops. It doesn't matter, because everything is grouped together on the inner term, I'm just summing a bunch of things. It doesn't matter what order I sum them in. Okay, so that's illegal for me to switch these there. Okay, now what I can see is actually this h of n doesn't depend on the inner sum. This h of n is a constant over all the n on the inner sum. So I can actually now, since h of j is a constant on the inner sum, I can factor it out. So it's like the distributive property in reverse. So what I can do is just write this as, so taking that h out, putting it here, that's all I did. Okay, now I'm getting close to something that I wanted in my proof. I wanted to say that yk was xk times hk. Well, I almost have xk here. So x of k is this sum, xn e to the negative I 2 pi k n over n. And I should also write that you know, h of k is the same thing, but over little h. Anyway, so I almost have this one, right? But instead of having xn times the phasor summed over all that, I have xn minus j. So I have to do something to change this to xn. Okay, so now what I remember is, okay, now I use the fact that x is periodic. And so shifting it by a certain amount only changes its face. Does not change anything else about it. So I'm going to jump back to module 11 and review this, because this is a really important key property here. Whoops. There's a lot of heavy GIFs here, or GIF. I don't know how you want to say GIF. So what we remember is, okay, let's say I have a pure sinusoid here. If I shift this, I'm only looking, I assume this thing is infinitely periodic, but I'm only looking at a little snippet of it. When I shift this, it doesn't change the amplitude It only changes the phase. Okay. And same thing with any signal. I'm assuming that it's infinitely periodic. I mean, some weird stuff can happen. This is the windowing effect that we talked about, but it only changes the phase of all the Fourier coefficients. It doesn't change their amplitude. The other thing to remember is that actually the phase of higher frequencies changes faster as we shift by the same amount. So let me just note that phase of, or yeah, so really we're gonna look at the formula. So recall the formula. Cos of 2 pi f t minus some shift. That is equal to cosine of 2 pi f t minus 2 pi f times the shift. Okay. So what I can do is use a similar observation to realize that actually this, so therefore, this is actually just going to be, it actually is almost what we want. This is the Fourier transform of x, but changed by a phase. And the phase would be negative 2 pi times f times j here. Okay, let me actually make this very explicit. So I'm shifting my signal to the right by j. So what I need to do is phase shift by that amount, negative 2 pi fj. Now phase shift, so since a phase shift in the complex DFT is simply a unit phasor, I can write this as a complex number. So that this is going to be xk times e to the negative 2 pi fj. Oh, actually, yeah, I've got this, sorry. Negative e to the negative I 2 pi, and f is actually k over n times j. All right, so I have this identity. Trying to get this to look nice here. That's supposed to be that. Okay, there we go. Okay, so nice. I can actually replace this entire inner sum with xk times this. So let me do that. So substituting this in, we have this, and I'm just going to substitute that in. So nice. I got this. This sum was nasty. I was able to now I'm able to get rid of it just by replacing that whole sum with this. So here's where we're at. Okay, now it seems like we're getting really close. So what I notice is xk is actually now a constant over this whole sum, so I can pull this out. So I can write this as xk times this whole sum. Okay, now, guess what? That's the Fourier transform of h, isn't it? I just use a different variable for my inner thing, but that's the Fourier transform of h. So actually I'm done. Ha! Nice. So y of k is equal to x of k, and then this sum just turns into h of k. Boom! There it is. All right, so that's the proof. Pretty cool, huh? So now I just want you to think about, now that you know this, I want you to think about something which is going to help us next week. And then I want to move on and just talk about one more thing, which is, okay, it's a bit of a nuisance that I did have to assume that xn and hn are periodic. Some weird stuff can happen if I'm not careful, and I do that in practice. I mean, the reason I did that is because they both had to have n samples. That's another nuisance. They both had to have the same number of samples. I'm just going to show you how to deal with that in the next module in practice. When you want, let's say you want a really short impulse response. Well, how do you get that to work? even if it has to be n samples. Okay. But anyway, I always thought this was like totally amazing. How you can prove this, and it really is a pretty short proof. The key trick was just switching the order of these summations and then realizing that because of my assumptions, I can assume that shifting a signal simply comes out as a phase, which actually I can write phase changes as a complex number. Those are the tricks. And then it's just rearranging things and just recognizing that I've got my formulas here. Boom. Boom. Okay. I love it. So let's let that sink in, do a little thought experiment, and then we'll talk about one more thing.